All right, so here we are in Chapter 10, Section 2, which deals with small sample inferences. And what we're going to be focusing on here will be the population mean. So we're going to be doing estimation here, all right? We're going to be doing hypothesis testing. So remember, estimation. Oh, let me get my black marker out. So with estimation, that's going to be a confidence interval. And remember, since we're talking about a population mean, we're going to be estimating mu. And then with hypothesis testing, okay, remember, there is a process in which we do hypothesis testing. So step 1, remember you want the null hypothesis, always contains the condition of equality. So mu is going to equal some value. We're going to call it the initial value of mu itself, all right? We also have step 2, which is going to be the alternative hypothesis. Now, that can take the shape or the form of less than, which is right tail. Mu could be greater than, which is going to be a left tail. Oops, sorry, I got them backwards. I'm so sorry for that. First one is left tail. Second is right tail. I'm sorry about that. And then the last form we can have mu does not equal the value, and that is our two tail. Okay? Step 3. Now, step 3 is going to be different here. Now, remember, we are working on the assumptions that we have a simple random sample and number 2 is that sample data come from a normal distribution. And if that's the case, and we could verify that, remember, verify using the QQ plot, which we call the probability plot, remember? That was in the previous video. All right. So if we can verify this, then step 3, which is our test statistic, all right, is going to be T equals X bar minus mu naught, which is our initial mu value that comes from our null hypothesis, all over S divided by the square root of N, which should look actually really familiar because this is basically the Z test or the Z test statistic. But with the T, you got to be careful because you got to remember your degrees of freedom equals N minus 1. So when you find your test statistic, all right, and you go ahead, and then you graph, you label critical values, and you conclude. You got to be really careful because you cannot use those Z tables or those Z values that we're really accustomed to because our T test statistic changes. We got to go with the degrees of freedom because that is going to dictate what our graph actually looks like. Okay? Now, if we wanted a confidence interval, okay, the interval is going to look like this. So we have X bar plus or minus T alpha over 2 times S over the square root of N, where T alpha over 2 is going to be determined with our degrees of freedom. So you got to remember, anytime you use that T table, we are talking about degrees of freedom. All right. So what I'm going to do here is we're going to do a couple examples. I'll do 1 or 2 using hypothesis testing. I'll do 1 or 2 with confidence intervals. And then I'm going to show you how to get a p-value because you got to be really careful with a p-value. In fact, I recommend if you're going to find a p-value, only use technology. Do not use your book or a table. And it's because we are really limited on the amount of t-values that we have because of the amount of variability. So it's always better just to use technology when you're using a p-value, but I'm going to show you how to do both, okay? All right, so here's our first example here. So we're going to do a hypothesis testing, and it's going to be sugar in cereal. I don't know about you, but I'm a huge fan of cereal. I tend to eat like 2 bowls of cereal before I go to bed almost every single night. And I'm going to be honest with you, I shouldn't be eating this, but I do like Reese Peanut Butter Puffs the best. But my wife, she will start to complain and say, you really shouldn't be eating that because there's too much sugar in it. And I will not disagree with her because she's right in that sense. But now I kind of switched to Honey Bunches of Oats, which is still pretty good, but it's no Reese Peanut Butter Puffs, let's be honest. So here we go. Let's do this problem. So different cereals are randomly selected, and the sugar content, grams of sugar per gram of cereal, is obtained for each cereal with results given below for Cheerios, Harmony, Smart Start, Cocoa Puffs, Lucky Charms, Corn Flakes, Fruit Loops, Wheaties, Captain Crunch, Frosted Flakes, Apple Jacks, Bran Flakes, Special K, Rice Krispies, Corn Pops, and Trix. We use a 0.05 significance level to test the claim of a cereal lobbyist that the mean for all cereals is less than 0.3 grams. So normally what happens here is this. And supermarkets are really smart about this. If you notice, if you walk down the aisle of the supermarket where the cereal is, all of your really sugary cereals, let's be honest, the ones that taste really good, are all in the middle shelf. And there's a reason for that. They're on the middle shelf because that is the average height of a kid. And kids, they don't want to eat Special K. They want Fruit Loops or they want Lucky Charms. Some of them even want Captain Crunch, which I think is crazy because I think when you eat Captain Crunch, it like cuts the roof of your mouth because those little corn puff things are really sharp. They got to do something about that. So a cereal lobbyist will come in and say, hey, listen, here's all these other cereals. Our cereal is not as bad as the other ones. That's what they try to do. So we're going to test this claim here. So test the claim, cereal lobbyist, that the mean for all cereals is less than 0.3 grams. We need a 0.05 significance level. So alpha equals 0.05 and n equals, I don't even know what n equals. Let's see here. 2, 4, 6, 8, 10, 12, 14. We have 16 cereals. All right. So step 1, our null hypothesis. Well, we know we're going to be testing the claim of the mean that's right here listed in our last sentence. So mu has to equal 0.3 grams because that's what this cereal lobbyist is claiming. So our alternative hypothesis is going to be mu is less than 0.3 grams. Now, if you're asking, where am I getting less than from? It's right here. Here are the words. Is less than. That screams alternative hypothesis there. Okay? Now, let's go ahead. Let's keep moving here. Oh, sorry. That was step 2. So step 3. Let's go ahead and let's identify all the important pieces of information. That way we can calculate our test statistic. Now, remember, since we have a small sample size here, we need to use t. So t is going to equal x bar minus mu all over s divided by the square root of n. So this is just our test statistic. So what we have to do, if you look in this problem, and this is going to happen in your homework, and it's going to happen on your test, I give you data, and it's a small data set. You need to know what S and what X bar is. So you're going to have to calculate that. So what I went ahead and did is I put it into Excel, and we're going to go ahead and we're going to calculate this stuff real quick. So let's see, our mean is going to equal, let me go ahead and just justify that. So this is going to equal the average, of all those values right there. All right, so our mean, X bar, is going to equal 0.295. And then the sample deviation is going to equal, so let me go ahead and just kind of give a little bit of a space there. We'll write justify. Now this, if you want to use Excel to do this stuff, I am 100% in your corner. But you got to know how to do it. So if you put an equal sign at the very start of a cell, this C3 is the cell. You can see it outlined in green. All right. you start it with an equal sign. In fact, maybe for this, to avoid confusion, I'll just get rid of these right here. I think that'll be fine. All right. So the sample deviation is going to equal. Now, if you start typing in standard deviation, okay, Excel has all these built-in functions, which will find it for you real fast. So I'm going to hit ST, and notice as soon as I hit ST, you got standardize, but then you have stdev.p. It's really hard to see that. I'm sorry. Let me see if I can. I didn't even notice it until I looked over. I'm going to try to zoom in as much as I can, but I don't think it's going to change much. Yeah, it's really hard to see on your screen. I'm really sorry for this. But if you just follow along with me in Excel, okay, and you hit equals ST, the first option says standardize. The second one says stdev.p. And then the third one is the one you want. The third one stands for standard deviation.s. The .s means sample. So stdev.s means sample. The other one would be for a population, which you do not have. So to help us here, all we do is just highlight all of our values, end the parenthesis, and just hit enter. And there's our standard deviation. So I'm going to go ahead and kind of just, oops, sorry. I'm going to make this a little bit smaller here. And I'm going to go ahead and on our notes, which you cannot see currently because I'm writing it down. In fact, let's draw this out a little bit. There we go. 0.1677299, because I'm a huge fan of decimals, because you got to be careful, because sometimes in your homework it says round to 2 decimal places or round to 4, and you cannot round until the very end. So here we go. We got our information that we need. So 0.295 minus 0.3 divided by 0.167729942 over the square root of 16. So go ahead and put that in your calculator. Make sure you get the same exact thing I get, which is negative 0.1192. So we'll leave it at 4 decimal places for now. Okay? So remember, this is our t-test statistic. Step 4, this is where everything comes into play now. All right? So we're going to draw our graph. Now, if you look at the alternative hypothesis, it's less than. So that means this is a left tail test. Our degrees of freedom is going to equal 16 minus 1. So degrees of freedom equals 15. With alpha equals the 0.05. And this is in one tail. Okay? We know anything to the left of our line is going to be the reject H0. Anything to the right will be fail to reject. The null. So the only thing that we got to do is just find that critical value there, which is on the left, so we know it's going to be negative. So what we're going to be looking up here, 15 degrees of freedom with alpha equal to 0.05 and one tail. So let's go back to our t-table. I'm just going to zoom in here for us. All right, remember, degrees of freedom equaled 15. Area and one tail. I already forgot what it was. 0.05 and one tail. All right, so 0.05 and one tail. 15 degrees of freedom. So if you look on the lower part of your screen, my critical value is negative 1.753. So let's go ahead and transpose that. Negative 1.753. Now, if you look at the test statistic that we calculated and plot it. So let's see, what was our test statistic? Oh, it was right here. Negative 0.1. Oh, so that's definitely going to be over here in our fail to reject. So our conclusion, We fail to reject H0. So if we want go ahead and just write a little statement that kind of summarizes what just happened here. There is not sufficient evidence to reject the null hypothesis. This means that the sample data supports the population mean for sugar in cereal is approximately 0.3 grams. So in other words, this lobbyist that's saying, whoa, our cereal's less than 3, it's going to be better, or less than 0.3, we can't reject the null. So we can't, our evidence that we collected does not support what he's saying. Okay? And that is basically one whole example in a nutshell. I mean, there's nothing different from chapter 10 versus chapter 9. It's just we're dealing in a different situation now. Okay? So let me go ahead. Let me do another example here for us. Oh, you know what? Before we go into another sample here, or another example, what I want to do is I want to show you how to use salt using this. Okay? So let me get out salt here again. All right? So we're gonna click on that. There we go. So here's salt. So luckily for us, all right, look at what our settings are here. So if you go over to inferential statistics, procedure selection, it's the very first one sample t. Now, according to the problem we just worked on, we know the sample mean is 0.295. Our sample standard deviation we calculated to be 0.167729942. And our sample size was 16. Remember, they're asking for sample size. They're not asking for degrees of freedom. Salt will automatically take degrees of freedom into consideration. All right? Our hypothesized mean was 0.3. And we are looking at the alternative hypothesis, which is less than. Now I'm just going to go ahead and click on Generate Results. Here's our null. Here's our alternative. Okay. The mean, 0.295, which is what we calculated. Degrees of freedom was 15. Here's our test statistic, negative 0.119236, which is exactly what we calculated. And like I said, here's our p-value here. So if you were to look up this test statistic of negative 0.119 on your t-table, you're not going to find it, which means you can't get a p-value. You can only estimate what the p-value is. So technology takes over that realm for us. So what I'm going to do here is I'm going to just copy and paste this and put this into our notes because I think it's really important. So give me a second here. Let me do that. All right, and just remember that if the P is low, the null must go. Well, when we compare our p-value, 0.0 or 0.45335 to 0. What was it again? 0.05. Definitely larger, which means we fail to reject the null, okay? Now, let's do another example here. Okay, so here's our next example. So use a 0.05 significance level to test a claim that the mean lifespan of cell phones is equal to 5 years. The sample data are summarized by the statistics n equals 27, x bar equals 4.6 years, s equals 1.9 years. And don't worry about the SPSS display on the next page because we're going to do it ourselves. All right? So step 1, Our null hypothesis, well, that's going to be mu is equal to 5 years. The alternative, which is step 2, mu does not equal 5 years. Now, if you're asking yourself, well, how did I get not equal to 5 years so quickly? If you read the question, the very first sentence says, test the claim that the mean lifespan of cell phones is equal to 5 years. Well, what's the opposite of equal? Not equal. This doesn't say anything about less than or greater than. It just says it's equal to. So what we need to do is be very careful and just say, okay, we're going to use not equal. We're going to use a two-tailed test. That way we cover all of our tracks. Step 3 is going to be our test statistic. So t is going to equal x bar minus mu over s divided by the square root of n. So for us, let's see here, we got 4.6 minus 5 divided by 1.9 over the square root of 17. All right. And if you do the math, you should get negative 1.0939, which we'll just call this negative 1.094. So there's our test statistic right there. So now step 4, let's go ahead, let's graph this. All right, so we know we have a two-tailed test. So alpha equals 0.05, but it's two-tailed. Our degrees of freedom, 27 minus 1, so degrees of freedom equals 26. So what we need to do is go into our table, look up 0.05, two-tailed, degrees of freedom, 26. So let's go ahead, let's do that. So let's see here. I'm going to zoom in for us. I'm going to get rid of this stuff. Don't worry about the right-hand side here. We don't need any of that. So remember, area in two tails, 0.05. That's what we're looking for. Now we need to go down until we see 26 degrees of freedom. So 26 degrees of freedom is right here. And if I just zoom out just a tad, 2.056 will be my critical values. So 2.056 positive and negative 2.506 negative for the left. Now, let's go ahead. We're going to label our test statistics. So that's right here, which is our fail to reject the null. So we can go ahead and just write a little conclusion. All right. We fail to reject the null. And then what we can do is just kind of just write a little statement about the claim that was labeled. So the sample data supports the claim that the mean lifespan of cell phones is equal to 5 years. Which, when you think about the cost of a cell phone, they're like $1,000. That's crazy. They should last more than 5 years. But Google, Apple, Android people, Samsung, they're very smart. And they know if you need a new phone every 5 years, they have a customer for life. So they design them to start doing things weird every 5 years. In fact, I don't know if you remember this, but a while ago, Apple was actually in a lawsuit and they lost because they deliberately would change their operating system so the battery life in older models would drain faster. So you would sit there and go, oh my gosh, my battery life, is terrible. Meanwhile, your battery life is fine. It's just the operating system, the way they designed the operating system for that phone told it to, okay, let's drain the battery faster now. And like I said, they got sued and lost, and they had to pay all this money back to people. So, just be careful. That's all. Now, The next problem I'm going to do is just a confidence interval. It's very straightforward. So let's go ahead. Let's look at an example like that. Oh, wait. I'm sorry. I got to show you the p-value. I didn't even do the p-value. I'm so sorry. So this p-value thing, we got to be careful with it. All right. Now, let me use a different marker here. Let's say you had no access to technology, okay? So you got to estimate what this p-value is. Now, our test statistic was equal to negative 1 point, what was it again? Negative 1.094. So we're going to take the absolute value of that because remember, that t-table deals with all positive values. So we're just going to call it 1.094, okay? Now, I'm going to take that number, and we're going to go back to the t-table here. All right, so here's our t-table. And give me a second here. I'm going to erase everything. All right, so I erased everything. Degrees of freedom equals 26. Our test statistic turned out to be 1.094. So what we have to do here, all right, is we need to go down to 26 degrees of freedom. I'm going to zoom out here just a little bit. So here's our row, which is 26 degrees of freedom. And remember, t equaled 1.094. So what we're going to have to do is we're going to have to find where that number falls in between. And remember, this is area and two tails, okay? It's going to play a major role in a second here. So if we scan across the row, 1.094. Let's see here. I got to scan across the row. So we have this value right here, which is 1.135. Now, remember, what we're talking about is 1.094. So if I go all the way up back to here, I can see that 0.2 corresponds to 1.315 as a t-value. In other words, right there is going to be our p-value. Now, we know, for example, that 1.094 is less than, let me write it like this. 1.094 is less than 1.315, which means our p-value is going to be less than 0.20, okay? Now, what really kind of makes this difficult is that we don't even know how far less it is, okay? But what we do know, it's going to be smaller than 0.20, all right? Now, that is our best guess right there. This is, like I said, this is our best guess. Okay? Now, the thing that we really got to be careful about is that since we are guessing this, all right, we have to basically write something that says, okay, our best guess is our p-value is going to be less than 0.2, but it's going to be greater than 0.05. Okay? Now, if you're asking yourself, which you should be, where did I get the 0.05 from? Remember, this was alpha that was given to us in the problem, okay? And we know we failed to reject the null, which means our p-value has to be larger than 0.05. Now, earlier, I made the comment, and I said we need to be careful because we got area and two tails. So this p-value, and I'm going to change my color real quick, is really 1/2 of the actual value. Okay, because remember, we have two tails here. So in order to find the actual true value where this p-value actually occurs, we're going to multiply this entire inequality by 2. So 2 times 0.05 is going to be less than our p-value, which is less than 2 times 0.20. So our p-value is going to lie somewhere in between 0.1, which is less than the p-value, which is less than 0.4. And that's our best guess. Okay? That is why technology really, really plays a huge role with this. So just to verify that we know what we're talking about here, okay? We're going to go back and we're going to look at these sample statistics, which we have here. All right? And we know our best guess for our p-value is somewhere in between 0.1 and 0.4. That was just using the table, which is, if you're stuck, that's what you got to do, and that's okay. But let's go ahead and let's use salt to actually say, okay, yes, we're dead positive that's in between these two things. So here we go. So if I go back into salt and type in all of our important information, our sample mean, 27. Oh, sorry. Sample mean is 4.6. The sample deviation is 1.9. The sample size was 27. We're doing a hypothesis test. The hypothesized mean is 5 years. And the alternative is not equal to. And when I generate the results, here's what we get. So let me go ahead and just copy and paste this into our notes real quick. And then we can talk about it. All right, so here it is, copy and pasted back into our notes. And I want you to look on the far right-hand side. Here's our p-value, 0.284. And if you think about it, with what we hypothesized, our best guess, our p-value definitely falls within that range of 0.1 to 0.4. So you got a couple questions, I think one or two, which deals with you estimating the p-value for a t-test. The method on how we do that is we look at, and I'm going to go back to our notes real quick. The way that we do this is we look at our degrees of freedom, and then we try to find, within that row, we try to find where that number falls in between. Okay? In this specific example, the lowest value that we could get is 1.315. Now, the classical approach, we knew that we failed to reject the null, which meant that our p-value has to be larger. All right? It has to be larger than 0.05, because remember, and I wrote it down in the previous problem. If the p is low, the null must go, okay? Our p-value is larger, so we failed to reject in the previous problem. Same thing here. When we did the classical approach, our test statistic was negative 1.094. We failed to reject, which I know, right then and there, I know our p-value is greater than 0.05. Like, I knew that, okay? So when we go to estimate it, we had to use that approach, which was... Sorry, I know I'm bouncing all over the place here. A lot of tables, as you can see. So I know our p-value got to be less than 0.2 because that is the column it had appeared in. But it also has to be greater than 0.05. Okay? And since I have a two-tail test, the p-value that we're going to calculate, or that we're going to find, is actually 1/2 of that p-value. So 1/2 times the p-value is going to be in between 0.05 and 0.2, which means I multiply both sides of this linear inequality by 2 to give us our best guess, which is our p-value should be somewhere in between 0.1 and 0.4. Using technology, we nailed it. We nailed it exactly where it needed to be. Okay? So now I'm going to show you how to do just one example to find a confidence interval. It's very straightforward. We have our formulas. It's just a matter of just substituting numbers in and then going ahead and reducing appropriately. All right, so here's an example here that deals with credit ratings. So when consumers apply for credit, their credit is rated using FICO scores. So it's the Fair Isaac and Company scores. Credit ratings are given below for a sample of applicants for car loans. We want to use the sample data to construct a 99% confidence interval for the mean FICO score of all applicants for credit. if one bank requires a credit rating of at least 620 for a car loan, does it appear that almost all applicants will be suitable for the credit rating? All right. So notice here we have a bunch of credit scores. Okay. And our goal is to create a confidence interval because we want to estimate. So let me write this down. So we want to estimate the average credit score of all applicants. Okay, that's the first thing we want to do. And then the second thing we want to do, if Bank A, we'll just call it Bank A, requires at least 620 for a car loan, does it appear that almost all applicants will have suitable credit ratings? All right, so here's what's happening here. You own the company. I don't care what company it is. We're going to call it Car Sales Owned by You. All right. And you've noticed that over the course of, let's say, a year or 2 years or 5 years, you've been accumulating this data on people's credit scores. All right. And you want to first estimate, well, what is the average credit score of all our applicants? And then you can use that information to go ahead and shop around for the best, I guess, bargain for people buying a car. And remember, when you go to buy a car, all right, and they run your credit score and they say, okay, here's what your payment's going to be, here's what your interest rate is going to be, that's because they have deals with the banks that they work with. You can always, have them look at other banks for an even better deal because, see, like I said, they have deals with banks. So they're going to go with those banks first. There's a lot of banks that exist. So you could say, you know what, those are pretty good. Can we broaden our search a little bit? And they're always going to say something along the lines of, well, you know, these are the best scores we can get because this bank works with us all the time and they give us the lowest rate. And you say, I understand that. I just want to broaden our horizons a little bit. Let's look at some other banks. That's the first thing. And the second thing is you can go to your own bank and say, hey, I want to purchase a car. Here's how much money I'm going to put down. Here's how much I need to finance. What can you do for me? And then you can use that and go back to the car dealership and say, well, my bank's going to give me this. If you can match this, if you could do better than this, we'll go with your bank. But if you can't, I'm going to go with mine. So you can always do that stuff. So what I'm going to do here is I'm going to go ahead, open up Excel, and we're going to get the important pieces of information here. Because remember, when we look at a confidence interval, when we look at a confidence interval from mu, we have x bar minus the margin error, which is less than mu, which is going to be less than x bar plus the margin error. And our margin error, you got to remember here, is equal to T alpha over 2 times S over the square root of n. And we need degrees of freedom here. So our degrees of freedom is going to equal n minus 1. All right? All right, so here we go. So here's Excel. I got the credit scores. How many credit scores do we have? N, and I'm going to go ahead and just justify this for us. All right, so here we go. So our mean. So the mean credit score is 660.31 with a deviation sample deviation of 95.89, and the number of samples here is going to be 16. Perfect. Now, what I'm going to do is I'm going to go ahead and I'm just going to round these numbers because credit scores are whole numbers. They always round up, which is kind of nice. So let's go ahead and there we go. So our mean is 660. Sample deviation is 96. Number of samples equals 16. So let me write this down real quick in our notes. X bar equals 660. S equals 96. And N equals 16. All right, so we can go back into our notes now. Here we go. And let's go ahead. Let's calculate our confidence interval. So the first thing we're going to do is find this margin of error. Now remember, we need T alpha over 2 times S over the square root of N. Now this T alpha over 2 number, we got to find that on the T table. We know we want and I think it's a 99% confidence interval. Let me double check real quick. Yep, here it is right here, 99% confidence interval. All right, so that means alpha is going to equal 0.01, okay? Now, if you're wondering how I got that, alpha is going to equal 1 minus the confidence level. So alpha equals 1 minus 0.99. Which equals at 0.01. And since this is an interval, remember you have a lower and an upper limit. So this is 2 tails. So 0.01 is the total area in 2 tails. So now if we go back to our table. Oh boy, this is going to be fun. Let me erase this real fast. Here we go. Sorry about wasting your time here. So our degrees of freedom equals 15, because remember, n minus 1, we had 16 samples, minus 1 equals 15. So here's our row. And we have area in 2 tails with 0.01. So we come straight down. And right here is our T alpha over 2 number. Sorry for the really fat marker. I didn't change it. But we have 2.947. So let's go back into our notes. Oh, didn't want to do that. Here we go. So the margin of error is going to equal 2.9. I already forgot. 47. Multiplied by our standard deviation, which is 96. Over the square root of 16. And if you multiply that out, you're going to get 70.728, which I'll just round it to 71. Therefore, our interval is going to be 660 minus 71, which is less than mu, which is less than 660 plus 71. So 660 minus 71 is going to be 589. And then 660 plus 71 is going to be 731. So right here, we can say we are 99% confident that the average FICO credit scores of all customers is in between 589 and 731. Okay? Now, the second part of the question was, well, if Bank A requires, so Bank A wants a credit score of at least 620, which means they want a credit score greater than or equal to 620. Okay? And I want to read the question one more time. Does it appear that almost all applicants will be suitable for a credit? Credit what? we'll have suitable credit rating. So the question is, if Bank A wants at least 620, do our customers fit what they want? Well, absolutely. Because 620 is definitely in between 589 and 731. So it looks like the customers that we are giving this bank fit their criteria of a credit score of at least 620 or more. Okay? So I hope this made sense. I'm going to show you how to do this in Salt real quick, so don't worry, I'm not going to leave you alone on that. So let's go ahead, let's look at this. All right. Now, I will tell you this. Our values are going to be slightly different. Why? Number one, technology is way better at estimating. And number two, we rounded very early in the problem because we were dealing with credit scores. And credit scores are whole numbers. So we're not going to get exactly the same thing. However, our numbers should be relatively close. So we are still dealing with one sample T. Our mean score was 660. The deviation was 96. The sample size was 16. Now, we need to check confidence interval, and we're going to change our confidence interval here to 99%. Now, when we generate results, we have a 99% confidence interval. And if you look from left to right, N, 16, the mean is 660, standard deviation is 96, degrees of freedom is 15. And look at our upper and lower limits. Our lower limit is 589.2, but if we rounded that to a whole number, it would be 589. And then the upper limit is 730.7, and if you rounded that to a whole number, you would get 731. So like I said, even though our values are just slightly different, all right, they're slightly different, we're still extremely close, okay? So I'm just going to copy this into our notes. All right, so here we go. And like I said, I just want to copy it into our notes because I wanted us to see that the lower limit and the upper limits are extremely close to each other, okay? That's how we do this, and to be honest with you, that is what happens all the time in science, in business, even in nonprofits. We need statistics to make good decisions, all right? So people, companies in general, will pay statisticians a decent salary to do exactly what we just did. And I've had companies in the past ask me to do this for them, and I've done it. Usually I do it just for friends and stuff like that because it's a lot of work to collect all this data, and I just don't want to do it, which is really bad. So I only do it for like friends and stuff like that. But in my research project when I was in grad school, this is exactly what I did. I just collected some data, had a hypothesis, made a claim, and then tested it to see what would happen. All right? So if you have any questions, just let me know. Good luck, and I'll see you in the next video. Bye.